Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. We will continue with the topic of mechanical properties of materials. We have already discussed the properties strength, ductility, brittleness and malleability of the properties of the materials. In this session we will discuss toughness, resilience and stiffness. Now toughness, it is the property of material. It is defined as it is the property of material by virtue of which a material absorbs maximum amount of energy maximum amount of energy before fracture. So this is the property of material which is made under action of energy instead of application of mechanical force. So we don't apply mechanical force to calculate the toughness, rather we apply energy to calculate the toughness. Here energy is basically in the form of kinetic energy, means if the material absorbs more energy before the fracture, so its toughness will be more. Let's say we take two plates, two identical plates, one is made up of glass and the other is made up of wood, and if we throw a stone on both the plates with same force and velocity, so means with the same kinetic energy, that is kinetic energy half mv square. So once we throw the stone with the same kinetic energy, we observe that the glass breaks but wood does not break. So this is because of the reason that wood has more toughness than the glass. So means, or in other words, wood can absorb more energy and the glass cannot absorb more energy. So we can say the toughness of glass is less than the toughness of wood. Now let's discuss considering a stress strain diagram, and in this stress strain diagram we take a small element under the curve of the stress strain of any arbitrary material. So the area of the element, let's say the area of element, that is E, we can calculate, that is sigma and d epsilon. Let's say this is the d epsilon and this is the stress. So we can easily calculate the area of this very element, and that is d sigma d epsilon. Further we can, if we integrate from 0 to the maximum, let's say the maximum strain, that is epsilon dash. So this would be the total area of stress strain diagram, Now if we consider the units, so units of this small elemental area, so this is the units of this Newton per meter square, and the units of epsilon are dimensionless. So finally the units of this elemental area are going to be Newton per meter square. If we see in terms of the energy per unit volume, in terms of energy per unit volume, so the units of energy we know the joules, that is again Newton meter per unit volume, so meter cube. So again we are having the units of this elemental area Newton per meter square or Pascal. So both the units are same. So the area under stress strain up to any point will represents the energy per unit volume. So the area under stress strain diagram up to any point represents in fact the energy absorbed per unit volume of the material. And if we calculate the area of stress strain diagram till the fracture point, till here, this is the fracture point, so that will be the energy absorbed per unit volume up to the fracture. So area under stress strain diagram up to the fracture would be area under stress strain diagram up to the fracture point is known as modulus of toughness. This is the fracture point. So area under the curve up to the fracture is toughness of modulus of toughness of that very material, and we know that modulus of toughness is the mere of itself the mere of toughness, means more area under the curve, the more modulus of toughness of the material. Now talking about resilience and proof resilience, these properties are also made under application of energy like toughness instead of using the mechanical force. But before that, it is important to understand the strain energy. So strain energy that is represented by capital U. So it is the energy stored in a body due to the deformation. If we compress a spring, for example, if we compress a spring, and due to this compression the spring will hold some energy, and spring can push any object by again using this energy. Let us now discuss how strain energy comes in any of the object or body. Once any material is deformed, means to cause the deformation some force is applied. So we can say the force has done some work on the material in the form of deformation of the object. Same work is in fact stored in the form of energy in that very body. That energy is known as the strain energy. Thus, strain energy is in fact strain energy in fact the work done for deformation. Here it is important to know that how load is applied. Now means the type of or the category of load. So if we discuss the type of loads, there are basically main three types of load. One is that is gradual load. In gradual load, the magnitude of the load is gradually increased from 0 to the maximum. Then we have a sudden load. If the intended load is applied at once on the component, this will be known as the sudden load. And then we have the impact load. Means once the load is dropped from some height on the component, and as a result the component and load will collide and a shock will produce. So this type of load is known as the impact load. So there are three main types of loads. Mainly the gradual load is used in our studies, like in universal tensile machine, the UTM, the load value is gradually increased. Now we will study the strain energy under application of gradual load. Let's draw load versus deformation diagram. In this case, if the material under consideration follows the Hooke's law, then the behavior of load deformation will be linear, as we are seeing in this deformation load diagram. This is a linear portion, and when we increase the load gradually, accordingly the deformation is also increased, and a point will come where the linear behavior will stop. Let's say this point is A. Till that there is a linear behavior between load and deformation, and this is known as the elastic limit. Means the material will give elastic behavior till point A, and after that there will be plastic behavior. And if we calculate the area under the curve, let's say if we calculate area under the curve of this triangle, so that is going to be half load into deformation. So now coming back to the resilience and proof resilience. So we define resilience as the amount of energy is the amount of energy or strain energy within the elastic limit within the elastic limit till any point till elastic limit. Now strain energy or the energy absorbed by component within the elastic energy, that would be the resilience. Now what is the proof resilience? Now this is defined as is the amount of energy or strain energy absorbed up to the elastic limit. Now the proof resilience is the area under the load versus deformation diagram up to the elastic limit till this point. Now this total is the proof resilience, whereas the resilience is the amount of energy within the elastic limit. Let's say we take this point, so this area is going to be the resilience. So the difference between the resilience and the proof resilience is this, that the amount of energy absorbed within the elastic limit at any point, that would be known as the resilience, and the amount of energy or the strain energy absorbed up to the elastic limit here, this is going to be the proof resilience. Now if we consider this using stress strain diagram, the strain energy per unit volume under the case of considering stress strain diagram, the strain energy per unit volume is known as the density. And if we calculate the strain energy up to the elastic limit, or we calculate the area under the stress strain diagram, it represents the modulus of resilience. So generally we can say the strain energy per unit area is known as the energy density. And if we calculate the strain energy up to the elastic limit, let's say this point shows the elastic limit, so this is the modulus of resilience. And this we can calculate as the area under stress strain diagram stress strain diagram up to the elastic limit. That is the modulus of resilience. And area under the stress strain diagram up to the fracture point up till here. So this total area is the modulus of toughness. Now resilience or proof resilience is very important for the property for the springs. Further important points are the toughness, resilience, and proof resilience deals with the energies of the materials instead of mechanical force. Now under the amount of energy within the elastic limit, as we discuss here, that is the resilience, and the amount of energy absorbed up to the elastic limit is the proof resilience. Further, the area under we can describe here the area under load deformation diagram represents the energy or strain energy and area under stress strain diagram represents the energy density. And area under load deformation diagram up to the fracture point is known as toughness, and area under stress strain diagram up to the fracture point is known as the modulus of toughness. Now let's discuss the stiffness. It is the property of material. Stiffness is the property of material by virtue of which a material resists deformation. Means more stiff material would be more difficult to deform, or we can say that if the material is easily deformed means the material is less stiff. So the stiffness can also be defined as the load per unit deformation. The load per unit deformation. Let's say if we require 1 millimeter, if we need 1 millimeter of deformation, and we have components of two different materials, let's say of same dimensions. Let's say we have component of material A and we have component of same dimensions of material B, and to achieve 1 millimeter of deformation of component A we require 100 kilonewton of load, and to achieve deformation of 1 millimeter for the case of component B we require 200 kilonewton of load. So we can say the component B is require more load for the deformation up to 1 millimeter. So it means the stiffness of component B is greater than stiffness of component A. It indicates that the component B will more resist to the deformation. Now with this we end our discussion here. Allah Hafiz.